Today you guys are going to learn about probability with cards, and so I have pulled up here a 52 card deck so that you can get an idea of what a deck of cards looks like in case you are unfamiliar with what a deck of cards looks like before we start this probability topic. So first thing I want to point out is that this is called the ace. So there are ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king in each suit. So there's 4 different suits, and within each suit they have each one of those cards, ace through king. These last 3, the jack, queen, and king, are called face cards. So anytime it talks about a face card, that's what it means, is that they have faces on them. There are 4 different suits like I talked about earlier. There's the clubs that looks like this little 3-leaf clover. There's the diamonds, all right, there's the hearts, and there are the spades. So this is the spade down here at the bottom. 2 of the suits are black, so spades and clubs are black, and 2 of them are red. The diamonds and the hearts are red. There are 4 different suits, and each suit has 13 cards in it. So this is called a deck of 52 cards, because 4 times 13 would be 52. Sometimes you hear people talking about the game 52 card pickup, which is when they throw a bunch of cards on the floor and then somebody else has to pick them up. That comes from the fact that there are 52 cards in a standard deck of playing cards. We don't see jokers here, so we're not going to talk about jokers in this deck. We're just going to talk about the cards themselves. So hopefully that gives you a little bit of background to see what these probabilities look like. So first, let's talk about what probability is. Probability is the number of possible choices, or the number of successful choices, divided by the total number of choices, or the total number of options. To give you an example, if I said, what is the probability if you choose any day of the week? What is the probability that you choose a weekend day? So essentially, the probability of choosing a weekend day, I'm just going to put weekend day as WD, the probability of choosing a weekend day would be the total number of possible choices for ways to choose a weekend day. So you could either choose a Saturday or a Sunday. Those are 2 weekend days. So Saturday and Sunday, that's 2 possible choices, divided by the total number of options for days that you could choose. So you could choose Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, or Sunday. So there are 7 total days in the week that you could choose, and 2 of them would be weekend days, which is the possible choices. So the probability of any day of the week being a weekend would be 2 out of 7. So that's essentially how probability works. A lot of times we'll talk about probability with playing cards. A lot of times we'll talk about probability with dice, like you see here. Probability goes on a scale from 0 to 1. So it's decimals in between 0 and 1. You can also convert them to percentages. So for example, 0 would be like 0%. And 1 would be like 100%. So for example, to look at some percentages in the middle of that, the probability of rolling a dice or a die and getting one of the faces, so for example, the probability of getting a 4 would be a 1 in 6 chance, because there is one side that has a 4 on it, and there are 6 sides total on a die. So you have a 1 in 6 chance of rolling the number that you want. 1 over 6, by the way, simplifies to be a decimal, which you could convert into a percent that's between 0 and 100. Flipping a coin, there are 2 sides of a coin. So if I want to flip a heads, there's one side that has heads, and there are 2 sides total. So the probability of getting heads by flipping a coin would be 1/2. And then last but not least, a 4 in 5 chance. So for example, if I wanted to choose one of these blue dots out of this group of 5 dots, there are 4 blue dots and there are 5 dots total. So I have a 4 in 5 chance of choosing one of the blue dots. So that kind of gives you an idea of what probability is. I hope it tells you the scale that we look at it on, from 0 to 1 or from 0% to 100%. And these fractions in between, you could put them in your calculator to get decimals and convert them to percentages if you would like. But most of the time we leave them as fractions. So let's come back to our game of cards to understand a little bit more about probability with cards. So the probability of drawing a 7. In order to calculate that probability, we need to look at 2 things. The first thing we need to look at is the total number of ways to successfully get a 7. So as I go through this deck, I'm looking for a 7, I'm looking for a 7. Oh, I found one, so I'm going to circle that 7 right there. Alright, and I keep looking through the rest of the deck, and I'm finding all of my 7s, because I want to find out how many total ways could I get a 7. So I could get a 7 of clubs, a 7 of diamonds, a 7 of hearts, or a 7 of spades. So there are 4 different ways I could successfully grab a 7 out of the deck. So I put the number of successful ways for me to do that on top. And that's divided by the total number of ways that I could grab any card. And if you look in this entire deck, and you remember earlier how many cards are in this entire deck, there are 52 cards in the entire deck. So there's 52 ways I could grab any card, and there are 4 possible 7s in the deck. So normally we simplify our fractions, so I need to figure out what number goes into both 4 and 52, and that happens to be 4. So 4 divided by 4 on the top would be 1, and 52 divided by 4 on the bottom would be 13. So the chances of me getting a 7 and pulling a 7 out of the deck would be 1 out of 13. And that actually goes for any card, so that's the same probability as grabbing an ace out of the deck, or grabbing a 2, or a jack, or a 9. So any of the individual cards all have the same probability, because there's 4 of every one of those in a deck of cards. Alright, let's keep going. What about the probability of grabbing a face card? So let's count how many successful ways I could grab a face card divided by the total number of ways I could grab any card. So there's 52 ways I could grab any card, and let's see how many face cards there are. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 face cards in the deck. So that's 12 out of 52. And again, we like to simplify these. So let me think about what number goes into 12 and what number goes into 52. That would be 4. 4 goes into 12 3 times, and 4 goes into 52 13 times. So the probability of grabbing a face card out of the deck would be 3 out of 13. Now hopefully that makes sense from earlier, because we just calculated the probability of grabbing a 7, and we said it was 1 out of 13, and I told you that it was the same probability for any card that you chose. So the probability of grabbing a jack is 1 out of 13, the probability of grabbing a queen is also 1 out of 13, and the probability of grabbing a king is also 1 over 13. And so I have 1 over 13, 1 over 13, and 1 over 13. So if you add those together, I'll write it right here, I have 1 over 13 probability for the jack, I have 1 over 13 probability for the queen, and I have 1 over 13 probability for the king. If you add all those together, you get 3 out of 13. So it makes sense as to why our probability works. And that kind of leads me to my next point, because my next point is going to be talking about getting this or this. And so anytime you see this word or, right, and so you want to write this down probably in your notes somewhere to make sure you have it. Anytime you see that word or, it means to add the probabilities together as long as they are mutually exclusive. But if they're not mutually exclusive, then you have to take out where they overlap. So that's probability of A and B. You'd have to take out where they overlap if they're not mutually exclusive. And this example we're about to do right now is an example of that. Because these things are not mutually exclusive, we'll have to take away where they overlap. So to do an example with you, it says, what's the probability of it being a Saturday in the month of January 2015 or being an odd day? So one of those two things has to happen. So let's look at Saturdays first, because Saturdays are easy. So here's all my Saturdays, the 3rd, the 10th, the 17th, the 24th, and the 31st. Those are all my Saturdays. So what's the probability of it being a Saturday or an odd day? So here's my Saturdays, and here are my odd days. There's 1, 5, 7, 9, 13, 15, 11 over here, 25, 19, 21, 23, 27, 29. So that would be a Saturday or an odd day. So if you look at the numbers that are not circled, they should be even days or, essentially even days that are not Saturdays. So 4, 6, 8, 12, 14, 16, 18, 20, 22, 26, 28, and 30. So those are even days, and they're not Saturdays, all right? So that's good that all those are not circled. So the probability of it being a Saturday or an odd day, we have to count all these ones that are circled. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there are 18 days that are odd days or Saturdays, divided by the total number of days in the month, which is 31. So the probability of it being a Saturday or an odd day would be 18 out of 31. And that actually does not simplify, so we'll leave it exactly like it says right there. So hopefully you can understand how these two things are not mutually exclusive, and that's because some of these days that are Saturdays are also odd days. For example, the 3rd is an odd day, the 17th was an odd day, and the 31st were odd days. So those three days right there were our overlap, right? They were Saturdays and odd days. So if we strictly followed this formula, we'd need to subtract out those overlaps so you don't double count them. But that's okay because we have a picture here so we could easily count them and not worry about the overlap. All right, so let's go back to our ors. This one says, what is the probability of getting an ace or a queen? So the good thing about this one is that these are mutually exclusive, which means if I get an ace, there's no way that an ace is going to be a queen. So there's 4 of those, and there's no way that a queen is going to be an ace. So there's this, and there's 4 of those. So the probability of getting an ace is 1 out of 13, and the probability of getting a queen is also 1 out of 13. So that would be 2 out of 13, right? Keep that in the back of your mind. Let's come back to that and see if it actually holds true that that's what we're looking at here. There are 4 aces, and there are 4 queens, so that is 8 total cards divided by a total of 52. And each of these are divisible by 4. So we can divide the top by 4, divide the bottom by 4, and I get 2 over 13. So notice that you could do it 2 ways. You could either add the individual probabilities together, so the probability of getting an ace plus the probability of getting a queen, and you get the same answer as whether or not you're just going to count up the total cards and simplify it from there. So you get 2 out of 13 either way. But that's the probability of getting an ace or a queen. Let's look at another one. What about the probability of getting a club or an odd number? Now these ones are not mutually exclusive because many of the clubs are odd numbers. 3, 5, 7, 9, those are odd numbers. So we need to be careful because these ones are not mutually exclusive, so we can't double count them. So let's go with club first. The probability of getting a club would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so there are 13 cards that are clubs. And then let's see how many odd numbers we have not circled yet. So 13 total. Now we go 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So there are 25 cards that are odd numbers or clubs. 25 cards that are odd numbers or clubs. So the probability of getting a club or an odd number would be 25 possible cards out of the total number of cards in the deck, which is 52. And that does not simplify at all. That stays 25 over 52. By the way, just a little side note, we don't count aces as odd numbers because aces don't actually have a number on them. They're aces, so they're a little different. We don't count them as a 1 or anything like that. All right, the last topic for today is going to be the probability of A given B. So whenever you see given, or whenever you see this line, I should say you should always think of given. So essentially this one is saying, what is the probability that A is going to happen given B has already happened? All right, so B is a thing of the past. What's the probability that A will happen given that that's already happened? Here's a little formula for it, right? It's the probability of A and B. So essentially it's the probability that both of those things will happen divided by the probability that B has already happened. I would write down that formula because it's a nice formula to have in your notes, but I've told you guys many times before that memorizing things is not my favorite thing in the world, so rather than memorizing a formula, wouldn't it be easier just to understand the concept of what's happening? So I'm going to show you guys the concept rather than how to use the formula for it. So this one says, what is the probability that you are going to grab a face card if you know that a black card was drawn? So let's look what's going to happen. if I know that a black card was already drawn, that means that I could not have drawn a red card. So I'm going to cross off all the red cards. All right, how many cards are left? If I already know that I drew a black card, that means I have a total of 26 cards to choose from. Because there are only 26 cards left now that I've crossed out all of the red ones. So the next question is, what's the probability that I'm going to get a face card? So let me see how many face cards I have not crossed out yet. So there are 1, 2, 3, 4, 5, 6. So the probability of drawing a face card would be 6 out of 26, given that I already drew a black card. Now 6 out of 26, I can divide both of those by 2. 6 divided by 2 is 3. 26 divided by 2 is 13. So the probability of drawing a face card, knowing that I already drew a black card, was 3 out of 13. So that's how conditional probability works, is that if you know something else already happened, what's the probability that this other thing will happen? And I could have used that formula, by the way. 6 is essentially, well, at least 6 over 52 is the probability of getting a black face card, right? And then 26, let me erase this a little bit. 6 over 52 is the probability that A and B happen, so that it's a face card and it's black. And 26 over 52 is the probability that it's black, which is what was on the bottom. And so it simplifies to the same answer. So I like doing it this way, but you can also use the formula if you like it that way. All right. This one says, what is the probability of getting a 3 knowing that you already have drawn an ace from the deck? What is the probability of getting a 3 knowing that you have already drawn an ace from the deck? I interpreted this one of two ways. So I'm going to show you both ways that I interpreted it, and then we'll see which one you guys think it would be. The first way I interpreted it was this. What is the probability of getting a 3 given that you drew an ace? Well, here's what first came to my mind. My mind said, okay, given that you already drew an ace, that means none of these could be possible. All right, so there are 4 cards to choose from. And my question is, how many of them are 3s? Well, 0 of those are 3s, right? If I already drew an ace from the deck, 0 of them could be 3s. So the probability of drawing a 3, if I already drew an ace, was 0. 0% or just 0 over 4. That was the first way that my mind interpreted it, which was that, you know, it's impossible to draw a 3 if you drew an ace kind of thing. But I also interpreted it another way. So this is one way I did. The other way I interpreted it was this way. I thought to myself, oh, maybe they mean you already drew an ace out of the deck and you took it out and you left it out. So let's say that I drew that ace out of the deck. How many cards are left in the deck? Now that I drew one card and it's out of the deck now, I can't look at that one anymore. Here, let me just cross it off altogether, right? I can't even look at that card anymore. If there were 52 cards and I took one away, now there are 51 cards. And now what if I want to know the probability of getting a 3 now that there's only 51 cards? So there are still 4 3s, and that would be 4 out of 51, which actually does not simplify. So I'm not sure which way this problem is meant to be interpreted. I'm not sure if it means conditional probability, which says, you know, what's the probability of getting a 3 if an ace has already been drawn, which would be 0. Or what's the probability of getting a 3 given that you drew an ace and left it out of the deck and go back to the deck to get another card, which would be 4 out of 51. Your final will not have that discrepancy, so I'm not sure, because this one doesn't have a specific answer to it, so I'm not sure which one it should be interpreted as. But like I said, your final will not have the discrepancy where you get a little confused by that. So that was the last slide for today. I do want you guys to work on your packet that I gave you. I haven't given you enough information to do all of it. If you want to try more of it, you can. But the page that the sub is going to pass out to you guys, I want you guys to work on numbers 82 through 87. And that's what I'm going to look at tomorrow when I get back. All right. Thank you very much.